Hey everyone, Masha's here, and today we'll be doing the 2023 Paper 1 Chemistry, for Biochemistry, I should add. Only 25 marks, and it's multiple choice, so you'll be alright. So yeah, I'll start wasting time, we'll get straight into it. So, first question, we have, which of the following compounds is the least ionic character? And what ionic character means in this context is how close they are to forming a ionic bond. Well, remember, folks, ionic bonds exist on a spectrum between ionic and pure covalent. So, pure covalent would be one where atoms share electrons equally. Ionic is when they physically yank the electrons on, but you can have in-between states. So, what does this jibber jabber mean? That means the way we determine the spectrum is the difference in electronegativity. So if the difference in electronegativity is 0, then both atoms will be pulling on the electrons the same to strength. So they'll share them equally between them. But if there's a massive difference, one atom will dominate the other and pull the electrons basically completely to their shell, rip it off the other atom, which is now an ion, which is what we call ionic. So basically, what we need to do is go to our data booklet, do a wee bit of scrolling, and accidentally make extra copies while I'm at it. Can never remember the exact page. Oh, here we go. It's page 12, and this will list all our electronegativities of our compounds. So if I just go and quickly do that, we can go and figure this out. So sodium iodide, we've got sodium, that's 0.9, and where's iodine? That's 2.7. So 2.0 take away 0.9 to 1.8. So I'm going to write 1.8 there. I'm going to look for the compound that has the lowest difference in electronegativity. Sodium fluoride. So we already know that sodium is 0.9. Fluoride, you should actually be able to remember this, but it will have a perfect electronegativity of 4. So if we take that away, we'll get 33.1. I mean, potassium iodide, well, that's 0.8. And then iodide is 2.7, so that would be 1.9. And potassium fluoride would be, again, it's 0.8, take away 4, so you would get 3.2. And as we can clearly see here, the lowest answer here, lowest difference in electronegativity is A, sodium iodide. That's our answer. In which the following compounds would hydrogen bonding not occur? So, hydrogen bonding, remember, only occurs when you have a hydrogen atom and it's going to be bonded to one of 3 elements. It's nitrogen, oxygen, or fluorine, because these have got very high electronegativities and they do cool things, right? So if we go through here, okay, well, hydrogen is bonded to nitrogen there, so I think we can consider that, yeah, this hydrogen bonding will occur in A. Same here, we've got an OH. This is ethanol. It's the same active ingredient in alcohol, alcoholic drinks, and yep, that's correct as well. We've got an OH. This one over here, we've got a nitrogen combined with a hydrogen. That's beautiful. So I think C will be doing as well. But D, oxygen is just connected to the carbon, so there's no actual hydrogen bonding, as the hydrogen is not connected to the oxygen itself. So D does not have hydrogen bonding, and it tells us we need to find something that won't occur, so it would be D. Move on to 3. Fats are formed from glycerol molecules and fatty acid molecules. The mole ratio of glycerol molecules to fatty acid molecules is what? Now remember, the way we can figure this out, this is probably one of those things you're just going to have to remember, but glycerol molecule itself is known as propan 1,2,3-triol, but essentially here it looks something along the lines of this. I'll draw the hydrogens just for clarity's sake, but as you can see here, we've actually got 3 attachment points, 3 hydroxyl groups that you can stick fatty acids on, because they've got the carboxylic acids can react with hydroxylic functional groups to create an ester link, which basically translates into is that this thing can accept 3 fatty acid molecules. So that means that it would be 1 to 3, right? Because every 1 glycerol molecule can make 3 fatty acid molecules. Cool. So we see. I'm going to sneeze. Before I do that, I'm going to do number 4. A reaction was carried out as shown in the energy diagram. As you can see here, we start at 150 kilojoules per mole, and then we do our reaction, and then we go down to, looks like 50 kilojoules per mole. And this will be an exothermic reaction because the amount of energy in the substance, the potential energy has been going down, so it must have gone to the environment. So which of the following has a value of 150 kilojoules per mole? This is the activation energy of the reverse reaction for emphatically change reverse or vice versa. So, well, let's go through them. Bottom up. We'll go through them. Activation energy of the reverse reaction. So activation energy would be the energy that's required to get to this peak, right? So that's going to be 50 up to 200. That's 150. So that's pretty. A is looking pretty good. I'm going to tick it, but just double check. We're going to do B, C, and D and make sure I'm going to say. So emphatically change of the reverse reaction. So if you're going backwards, what there would be change in energy would be, well, you're going from 50 to 150, which would be 100. So I'll go write this in. 100 down here. And 100 does not equal 150, so and then we're going to have activation energy of the forward reaction again. So this is like going from here, and you want to go to this peak. So you're going from 50 to 200, which is of course 50. So 50 does not equal 150. Don't really need to tell you that. And then emphatically change of the forward reaction. That's this distance here again, 150 down to 50, which is another 100. So all of these do not equal 150, so we can be pretty sure it is going to be A. Moving on to number 5, the graph shows how the rate of reaction varies with the concentration of one of the reactants. What was the concentration in moles per litre when the reaction time was 10 seconds? Now note, on the graph you can clearly see there's actually no 10-second mark, because that is measured in relative rate. So what we need to do is transcribe this 10 into relative rate, and you can calculate rate as 1 over time, which is 1 over 10, which is 0.1. So we need to look at 0.1 on this graph, and we can see, okay, it's here, and we're going to need to go down to concentration, and we think, okay, well, it's going to be 0.25. And yep, that is the correct answer. Moving on. The diagram represents the change in concentration of a reactant against time during a reversible chemical reaction. In what diagram does the dotted line show the result of repeating the reaction using a catalyst? Okay, so if you use a catalyst, remember, you're going to be speeding up the reaction. But the catalyst is not involved in the reaction at all. It's not like you're providing extra reactants. So that means that the concentration will stay at the same level, but it will go down there quicker. So you'd end up with a line that looks a bit more like this. But so it's got a lower gradient, so it goes faster, but it doesn't go below the original line. So you can go down here and have a look. So this one here, well, it's going slower, and it's going to it's like you take away some reactions. So A is garbage. B is looking pretty likely. It's the same amount of reactants being used, but it goes faster. I'm thinking that might be right, but we'll just double check the other ones. This one, C is like if you added more reactants but kept the reaction rate mostly similar. So yeah, C's got bad, got a bad, and D is just it being it taking slower, which is like, well, if you did it with a catalyst, then you'd be faster. So yeah, it'd be B. Move on to 7. The enthalpy of combustion of methanol is negative 726 kilojoules per mole. What mass of methanol has to be burned to produce 145.2 kilojoules? Okay, so this is going to be doing some fancy pants formulas here. So remember, enthalpy is energy over number of moles. So we want to go and calculate the number of moles, because then we can use it to calculate the mass. So we're going to plug in some numbers here. So it'll be 145. Where's I can write 145.2 over n, and then the enthalpy change is negative 176. And we won't worry about the minus signs too much. I'll go to open my calculator. So what I'm going to do here is then rearrange this. So it'd be N equals 145.2 over minus 726, but minus signs does not matter at this point. You're not going to get negative energy unless you're doing something stupid with the Casimir effect. So I'm just going to ignore that. And we're going to get 0.2 moles. Now all we need to do here is go and calculate the mass from that. So 0.2. Don't know what the mass is, but I do know what the formula mass is. It's 32. So the mass would just be 0.2 times 32, which would be 6.4. And once we've done that, we can go over here and see what number we get. We'll let it, and it'll be B. Fantastic. Which of the following statements is true? The sodium atom is larger than the sodium ion. The chloride ion is smaller than the chlorine atom. The magnesium ion is larger than the magnesium atom, or the oxygen atom is larger than the oxide ion. So, where I'll do this is I'm going to go find where I put my data booklet. Here we are. Snap it to the side again. So, what we can do here is we can go over to periodic table, and this will show us all our different electron arrangements. So the sodium atom is larger than the sodium ion. Let's go and check that first, see if it's right. So sodium atom is a thing of 281, but if it was ionized, it would go to 28. So it would have one less electron shell and should be smaller. So A is looking kind of likely, maybe, but let's go and check the other ones. Chloride ion is smaller than the chlorine atom. So chlorine is over there. If we ionized it, it would be 288. So it would be slightly larger because there's more electrons repelling each other, kind of pushing it out. So that means that the chlorine ion would actually be bigger than the chlorine atom. It can't be B. Magnesium ion is larger than the magnesium atom. We'll scroll over to magnesium over here. If we ionize it, it would be 28. We're missing a whole electron shell compared to the atom. So that means that it can't be C. And then the oxygen atom is larger than the oxide ion. If we go over here, we have 2,6, and if we ionize it would be 2,8. So the oxygen ion would actually be larger than the oxygen atom. So all I have to say is that A is the correct answer. Which of the following structures is never found in compounds? So remember, a compound is when you just have a molecule made out of more than one element. So have a look through here. Right, well, I mean, the answer should really jump out of you here. It'd be C, wouldn't it? Because C is monoatomic, which means there's not even any bonds. It's just kind of free-floating atoms going on. You already find this in the noble gases on the very right side of the periodic table. So yeah, it would be C, but I could change the other one. So like a covalent molecular, well, that applies to water, you know. Water is a covalent molecular compound. And yeah, it's compound. It's got oxygen and hydrogen in there. Covalent network, because carbon is not a compound because of its carbon and diamond is not a compound because it's just one element. But you do get silicon oxide, which is like in glass and whatnot, which is a covalent network compound because it's got silicon and oxide. And then ionic. Well, that whole point of ionic is that you have atoms with different electronegativities, which would be different elements, which would be in compounds. So monoatomic is the correct answer there. Which of the following carbon-containing compounds is an isomer of hexanal? Okay, so remember hexanal? That would be I won't draw all the hydrogen because there's like 5 bajillion of them. But you'd have 6 carbons in here, and then you have a carbonyl group on the very end. So you have a double bonded oxygen. So what we're going to do is convert this into a molecular formula. So we have 6 carbon atoms, hydrogen atoms. Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yeah, it'd be 2N, wouldn't it? And then there we are, in really poorly drawn form. I'm sorry. So now we have a molecular formula. We can kind of go through here and see if there's any of these make any sense. So well, A is already off the bat for me because methyl, that's 1, butanol, that's 4. 1 plus 4 is 5, which is not 6. So we can cross that off. 3-methyl pentone, 2, 1. Maybe that actually might be correct because methyl plus pentan, that's 6, right? And then it's a branch chain, but that doesn't really matter in terms of isomer. And then it's a 1, which is, all ketones are isomers of alkyls or aldehydes. So B is looking pretty likely. Might be B. Let's look at the other ones though. So dimethylbutane, that those add up to 6. There's enough 6 items in here, but it is a alcohol, which would have a 1 extra hydrogen. No, actually 2 extra hydrogens in its structure, because you would, instead of having the double bond with OH, you would actually have a OH group. So not only are you having an extra H there, but you also have free up another one for another hydrogen. So that means that it can't be C. And then we have 3 dimethylpentyl. Well, 2 right there, because that's 2 times 1 essentially, plus 5 is not 6, so it can't be D. So that means it must be B. Move on to 11. When 2 amino acids react in a condensation reaction, water is eliminated and a peptide link is formed. Which of the following represents this process? So all these things circle the exact same atoms that would make water, but we need to make sure that we're picking the correct ones. So remember, an ester link is a amide link is kind of just very similar to an ester link. It looks a bit something a bit like this, and then yeah, there's a hydrogen up there somewhere, and then continues on forth. Yeah, I'm not going completely nuts there, am I? So what do we need to figure this out? Well, I mean, we've still got this double bonded oxygen, right? So that means that A doesn't like it because it's going to ruin this double bonded oxygen, and that's not what we want. And also it has to be with a nitrogen, which means B, where it's reacting with a normal, with a carbon, a hydrogen or a carbon, doesn't seem likely either. So C is looking pretty promising because it's got nitrogen, and it's reacting with the nitrogen hydrogen, and then it's reacting with the OH group, so maybe it might be C. And then for D, well, it's reacting with an alcohol group. It's the same molecule, the same functional group reacting with itself. Not correct. So it's going to be C. Number 12. Which of the following equations represents an enthalpy of combustion? Now remember, when we do enthalpy of combustion, what we want is, I'm going to write it out, complete combustion. So when we say complete, that means there's no, everything reacts completely, there's no weird semi-reactions, and we'll get into that, right? Because it's a complete reaction with oxygen of 1 mole of fuel. So using that like golden rule, we can go and figure this out. So already, A's garbage are usually 2 moles of fuel. B, maybe it looks promising. You've got 1 mole of fuel. It's reacting with oxygen. But carbon monoxide. Horrific. Which carbon monoxide is only generated during incomplete combustion, because you're supposed to get carbon dioxide, not carbon monoxide. So B can't be right either. C, 2 moles of fuel. Horrific. Can't be having that. And we go on to D, 1 mole of fuel, carbon dioxide, complete combustion. It's D. Move on to 13. 2 flasks A and B were placed in a water bath at 40 degrees Celsius with ethanol and ethanoic acid and ethyl carbonate and ethionate and water. After several days, the contents of the flasks were analysed. Which results would be expected? So flask A contained ethyl carbonate, water, ethanol and ethanoic acid. Flask B is unchanged. Well, and then so on and so forth, all different combinations. So remember, when you have a condensation reaction, so I'll go and write out the condensation reaction I'm writing here. Oh, piece of this, I'll type it out. No one will be able to read it otherwise. But ethanol, I'll just use words because I'm ethanoic acid. Would give you ethyl ethanoate plus water. So this is the reaction that we're talking about here. So you would think that you would just flask A and B would be eventually the same as A goes transforms slowly into ethyl ethanate and water. But don't be fooled. Yes, you'd think it would be B, but remember, this reaction is actually a reversible reaction. So I don't think there's a. So I'll have to do this. You should see this symbol where it's like 2 arrows going there. So it not only can you react ethanol and ethanoic acid to create ethyl ethanate and water, but it can go back the way as well in a hydrolase reaction, the opposite of condensation, which basically means that over time these would slowly devolve into mixtures of ethanol, ethanoic acid, ethyl ethanate, and water, so until they reach a dynamic equilibrium where the rates of all the opposing reactions are the same. So that means that it doesn't change anymore. So that means we're going to have to pick the one that says flask A and B both contain ethyl ethanate, water, ethanol, ethanoic acid. Ooh, that was a long one. 14. During a redox process, an acid solution, iodate ions are converted into iodine. You can see that got like a half-finished iron electron equation here. What value of x is required to balance the equation? So what we're going to do that is charge has to be identical on both sides. You can see here that it's neutral charge, but over here we've got 2 minus and then plus 12 positive, which means we'll be 10 positive effectively. So we need to equalize that out with 10 negative here. So that means x must equal 10. And it would be C. A step in the synthesis of vitamin B3 is shown. What name is given to this type of reaction? So we can see here that with we're turning what's basically an alcohol into a carboxylic acid. So what would be this type? Well, it's not going to be condensation. Condensation is when you react two molecules together and you join them together with a release of a small molecule, usually water. I don't see that anywhere, so we'll get rid of it. Hydration, well, yeah, but there's no. I don't see you're not actually adding any water to this. Hydrogen's getting removed and you're adding an oxygen, which is not really that either. Reduction, well, no, because remember, you have this kind of oxidation chain when you have an alcohol, and then you oxidize it. Oh, that's a clue. Maybe it's oxidization. You can oxidize it into a aldehyde or ketone. And you can further oxidize it if it's an aldehyde into a carboxylic acid, so just write acid because I'm running out of room. And well, yeah, reduction will be going further along the stage. Would be going backwards, so you'd be like turning the alcohol back into a carboxylic, like a carbohydrate. That's not really something we do. So reduction is out the table, and oxidation, when you're going to turn from an alcohol into an aldehyde into an acid, is correct. Right, I'll move on to 16. 16. A chemist analysed a mixture of 4 dyes, A, B, C, and D, using gas-liquid chromatography. The time taken to travel through the column, retention time, depends on the polarity of the molecule. The more polar the molecule is, the longer the retention time. The following chromatogram was obtained. Which of the following compounds corresponds to peak Z? Okay, so these are all the dyes to be put in, and the longer the retention time, the more polar the molecule is. So we'll have a look at D. Well, it's probably not going to be Z because it's one of the lowest retention times. It's very, very polar. Look at all these polar bonds. We've got hydrogen bonds all over the place. So we'll actually find the thing with the least polarity. And well, the answer jumps out at you right here. This is B is the only one that even lacks OH bonds. So I would say it is B. Number 17, the apparatus was used to measure the enthalpy of combustion of ethanol. We've got a thermometer, copper can, 100 cubic centimeter of water. Which of the following would not improve the accuracy of the result? So you're looking for stuff that you would not want to do, stuff that's kind of garbage. So using a Draught shield is a good idea. So you would a Draught shield would stop the energy radiating from the into the environment as much. Moving thermometer is not a good idea, because if you move a thermometer, it is a good idea. I mean, because if you move a thermometer, you'd get a better reading of the overall value of water rather than just a small component. Using a glass beaker instead of a copper can is a terrible idea, so it might be our right answer, because a copper can has better conductivity, while glass is more of an insulator, which means you're not getting all the heat that you want. And stirring water again helps all the heat kind of radiate outwards and heat up the whole water rather than just a small portion of it. So that is a good idea. So the only one that is terrible is C. You don't want to use an insulator when you don't have to. Number 18, which line in the table best describes the ball-like structures formed when soap is added to an oil and water mixture? So, got here, and it's all these little, we call these mycelials, which are little balls made out of these soaps. They use to trap oil and whatnot, and they're really good use for cleaning. So, the structure of these mycelials are made out of lots of these chains, which they've represented here. And the important thing to notice is that the head is ionic or polar, and it's therefore hydrophilic. So it dissolves in water very well. Oh, that was terrible. And that's because polar molecules dissolve other polar molecules, and so if you want something that if you make the head ionic or hydrophilic, if I can actually spell it, then that means it will dissolve easier. And then you also have this long tail here, which is non-polar, and is therefore hydrophobic. You can read that right, hydrophobic. And won't dissolve in water, but it will dissolve in oil, which is what we try and get rid of. So if we apply this, we just need to go and basically find which one of these sentences says. So non-polar head dissolves in water. Non-polar head, so A is garbage. Ionic head dissolves in water, that's correct. Non-polar head does dissolve in water droplet, and it is arranged correctly, because this is outside as water, so you want the head outside and tail inside. So B is looking pretty solid so far, but let's have a look at the other ones. So non-polar head dissolves in oil. Well, the head is not polar. The head is polar, so this is garbage. And then ionic head for D. Ionic head dissolves in oil droplet. No, oil is non-polar, so you wouldn't want an ionic head. So it has to be B. Moving on, we have number 19. In an experiment, nickel oxide is acted as a ferric acid until no more nickel oxide reacts. The products are nickel sulfate and water. The correct method to separate and collect a dry, pure sample of nickel sulfate is what? So, what we're going to have in our solution, because we want to just get nickel sulfate and filter out everything else. So that it looks like it should be fine, because we should just be able to have nickel sulfate and water, and we can just dry that, right? Well, what we're going to have to do is do something a bit hard and more difficult. And the way I'm going to do this is pull up our daybook and go to my favorite page, actually. Oh, you're going to be so excited with this. It is this table here. Wow, beautiful. So let's look at nickel oxide here on this table. Nickel oxide is insoluble in water, which means it's going to be a precipitate. It's going to set around in the water produced. So that means we're going to have to filtrate it first. So already we can't just evaporate it. We can't evaporate it and filtrate it. We have to filtrate it first to get rid of the excess nickel oxide that's still in the solution. But they're products of nickel sulfate and water. But if you look at nickel sulfate, it is very soluble. So it's going to be dissolved in the water of this reaction. So that means the only way to get rid of water and just get the solutes, we're going to have to evaporate it. So it's going to be filtration followed by evaporation, or C. Right, move on to number 20. Which of the following compounds will react with sodium hydroxide to form a salt? Okay, so sodium hydroxide solution, that's going to be a alkaline solution. So what we're looking for is a acid on this side. And I only see one that jumps right out is B, because got this COOH group here, which is I'll quickly draw it out for you, but it's a carboxylic acid group, but the name suggests, it is makes stuff acid, because this molecule here is basically makes H plus ions, which makes things acidic, and all the rest here are just, that's an alcohol, that's not acid, that is that's a ketone, not an acid, that's an aldehyde, not an acid. Only this one is an acid, and then you could make a neutralization action to form a salt. Which structural formula represents a primary alcohol? Now, a primary alcohol is one where the OH group is bonded onto a carbon, which is only bonded to one other carbon, i.e. it'll be on the terminal ends. So once we know that, we can just go straight through and be like, okay, well, it's going to be D because it's bonded to a carbon, which only bonds to one other carbon. This one here is bonded to this one's carbon is bonded to 3 other carbons. This one's here is bonded to 2 other carbons, and the same for this one. So the answer is D. 22. Reduction of 4-methylpentyl-2,1 to the corresponding alcohol results in the molecule either gaining 2 grams per mole, losing 2 grams per mole, losing 60 grams per mole, or not changing in mass. So if we're going to reduce this into an alcohol, what's going to happen is double bonds carbonyl group will be transformed into a COH group, and there will be an extra hydrogen atom on top, because you've freed up a bond. You're no longer double bonded with the oxygen, which means you've got 2 extra hydrogen atoms getting in. Well, and each hydrogen atom is 1 gram, one atomic mass of 1, so that means you're gaining 2 grams per mole. You're not losing it because you're gaining, you're not losing 16, and you are changing mass, so it has to be A. For 23, which of the following gas samples the same volume as 16 grams of oxygen? All volumes measured at the same temperature and pressure, which means this, if you have, I have 1 mole of carbon dioxide and 1 mole of chlorine gas, even though they've got different weights and masses, they all take up the same volume because it's measured at the same temperature and pressure. So what we're going to do here is calculate the number of moles in 16 grams of oxygen. Now oxygen, 60 mass, and then remember, oxygen is a diatomic element, so it's usually just 16 grams per each atom. Because it's diatomic, it actually goes up to 32, and that means we have 0.5 moles. So that means we just got to go through here and see if we can find anything. I think that's so we're going to have to go and calculate the formula mass of all these. So carbon monoxide, I'll go and pull up my table again, and we'll go to our mass page. So start with carbon monoxide, and so that's basically 12 plus a single oxygen, so that would be 28. Because that's 12 plus 16. Carbon dioxide, that's just the carbon dioxide with an extra oxygen atom, so we're adding another 16 onto that. So that would be, mental mass is 44. Nitrogen dioxide, so nitrogen is up here, and it is 14. 14 plus 2 oxygens, so that's 14 plus 32, so that's 36, 46. And then finally we have dinitrogen tetroxide, that's 28 for the dinitrogen, and tetroxide, that's 4 oxygens, so that would be 32, 64, which would be 72, 92. Fantastic. So now we've got to find out which one's a half. Well, 21 grams of carbon monoxide. That's that's not 1 half of 28. So no. 44 is not 1 half of 44. 46 is not 1 half of 46. But dinitrogen tetroxide is 92. 46 is 1 half of 92, which means it's got to be D. Right. Onto the penultimate question now. The number of moles of positive ions in 0.25 moles of aluminum sulfate is what? Okay, so this one, what we're going to have to do is figure out the composition of aluminum sulfate. So if I go down here, you can please see clear as day that aluminum would have if you ionized it, you turn it to 2H, would have 3 negative, right? So I'm going to write that down. Make it a bit bigger, maybe that might be an idea. Right, and then sulfate, I'm going to go scroll up a bit. down, actually, it's way further down. Here we are. Sulfate has -2. So it has to be chemically neutral, so we're going to have to equalize this all. So that means I'm going to put 2 aluminum and then 3 sulfate. So that'd be 2 times -3, that's 6, and it'll be positive 3, wouldn't it? And then you have 3 times -2, which would be -6. So -6 minus 6 would be 0. Okay, so that means that we're looking for positive ions in 0.25 moles. Deal with the sulfate a bit later. So we have 2 in each mole of aluminum sulfate. We have 2 positive ions, but because we're only dealing with a quarter of that, we're going to times 2 by a quarter, which is a half. So it would be A, 0.5. And last question: addition of the hydrogen chloride HCl to an alkane can give a mixture of 2 products. The product produced in the greatest amount in the reaction is called the major product. The major product is formed when the hydrogen atom of HCl attaches to the carbon atom of the double bond that has the greatest number of hydrogen atoms attached. The major product in the reaction of HCl with the 2-methylpentane-2-ane is what? Okay, so got methyl-2-ene here, and we've got to see what happens when we attach HCl. And it says it's formed when the hydrogen atom is attached to the carbon atom of the double bond that has a greater number of hydrogen atoms attached. So if we look at here, which carbon atom has the highest number of hydrogens? Well, this one has 0 hydrogens connected to it, and this one only has 1, which means it's going to attach to this one. It's a hydrogen atom, which means we're going to have the chlorine atom here, and this double bond is obviously going to be removed. So we'll go and have a look down here so you can find A. So that's swapped around. That looks correct. That's 2 chlorine, that's 2 hydrogen. So it's going to be B. Right. That's a shorter video than I thought it was going to be. I thought it was going to be a bit longer than this. But yeah, that's the whole 2023 Higher Chemistry Paper 1. And I'll be doing there'll hopefully be a link in the description to 2023 Higher Chemistry Paper 2. But who knows? I'm a bit very unorganized. But thanks very much for watching or tolerating me. And I wish you very good luck on your exams. MASH out!